In this video, we will derive the equations of relative motion for particles. When analyzing dynamic systems, it is often convenient to measure the motion of a body from a fixed reference frame, that is, a reference frame that does not move relative to some point in space. However, sometimes it is convenient to measure the motion of a body from a moving reference frame. A common fixed reference frame is that of a person standing still on the surface of the earth. So let's say a person is standing with his or her feet planted firmly on the ground. The person's point of view represents the fixed reference frame. Now, two cars move away from the person at different speeds. From the person's point of view, the blue car moves with a velocity of -3 miles per hour to the left, and the red car moves with a velocity of +10 miles per hour to the right. The velocity of the person from the person's point of view is, of course, 0 miles per hour. Now let's change perspective and examine the velocity of the three objects from a reference frame attached to the blue car. From the blue car's perspective, both the person and the red car appear to be moving in the positive x direction. The person moves with a velocity of +3 miles per hour to the right, and the red car moves with a velocity of +13 miles per hour to the right. The velocity of the blue car in this reference frame is 0 miles per hour. Finally, let's change perspective again and examine the velocity of the three objects from a reference frame attached to the red car. From the red car's point of view, both the person and the blue car appear to be moving in the negative x direction. The person moves with a velocity of -10 miles per hour to the left, and the blue car moves with a velocity of -13 miles per hour to the left. The velocity of the red car in this reference frame is 0 miles per hour. From this simple example, it is clear that the velocity is relative to the observer and that we must specify the reference frame when discussing the motion of bodies. Now we're going to generalize the position, velocity, and acceleration of two bodies relative to one another in a two-dimensional plane. Let's say there's a fixed observer at point O who is watching two bodies, A and B, travel through space. We'll make point O the origin for this fixed reference frame. Let the location of particle B be the origin for another reference frame which is moving along with the particle. We'll assume that neither reference frame is rotating. The position of particle A from the fixed reference frame is the vector RA. We say that RA is the absolute position of particle A. Similarly, the position of particle B from the fixed reference frame is the vector RB, and we say that RB is the absolute position of particle B. The position of particle A relative to particle B is given by the vector RAB. Using vector notation, RA equals RB plus RAB. Recall that velocity is the rate that the position vector changes with respect to time. So if we differentiate the relative position equation with respect to time, we obtain the equation for relative velocity. The velocity of particle A is equal to the velocity of particle B plus the velocity of particle A relative to particle B. Keep in mind that VA and VB are the velocities of the two particles as observed from the reference frame fixed at point O, while VAB is the velocity of particle A as observed from the moving reference frame located at particle B. Recall that the acceleration vector is the rate velocity changes with respect to time. So if we differentiate the relative velocity equation with respect to time, we obtain the equation for relative acceleration. The acceleration of particle A is equal to the acceleration of particle B plus the acceleration of particle A relative to particle B. AA and AB are the accelerations of the two particles as observed from the reference frame fixed at point O, while AB is the acceleration of particle A as observed from the moving reference frame located at particle B. As a side note, we can obtain an interesting result if we take the relative acceleration equation and set the acceleration of particle B to 0. AA, which is the acceleration of particle A as observed from the fixed reference frame, becomes equal to AAB, which is the acceleration of particle A as observed from the moving reference frame located at particle B. This means that the acceleration of a particle is the same in all reference frames that are not accelerating, and these reference frames are given a special name. They're called inertial reference frames. Earlier, we arbitrarily selected particle B as the origin of the moving reference frame. Let's see what happens if particle A were selected instead. RA and RB are the same as before because these are the position vectors of the two particles from the fixed reference frame. RBA represents the position of particle B from particle A's point of view. Using vector addition, we have RB equals RA plus RBA. Differentiating the equation with respect to time, we obtain the equation for the relative velocity, VB equals VA plus VBA. VB and VA are the velocities of the two particles as observed from the fixed reference frame at point O, while VBA is the velocity of particle B as observed from the moving reference frame located at particle A. If we differentiate the equation once again with respect to time, we obtain the equation for the relative acceleration. The acceleration of particle B is equal to the acceleration of particle A plus the acceleration of particle B relative to particle A. AB and AA are the accelerations of the two particles as observed from the fixed reference frame at point O, while ABA is the acceleration of particle B as observed from the moving reference frame located at particle A. Now let's compare the relative motion equations derived for both scenarios. We can eliminate RA minus RB between the two position equations, and we obtain RAB equals negative RBA. Similarly, we can eliminate VA minus VB between the two velocity equations, and obtain VAB equals negative VBA. Finally, we can eliminate AA minus AB between the two acceleration equations and obtain AAB equals negative ABA. This means that each particle sees the other particle at an equal and opposite position, and each particle appears to move with an equal and opposite velocity and acceleration. In summary, the relative position, velocity, and acceleration between two particles can be determined by knowing those quantities from a fixed reference frame. Each of these equations can be broken into their x and y components, so the three equations are really 6 equations, 3 in the x direction and 3 in the y direction.